Hello everyone, today I would like to present the demonstration of an arbitrary two-photon polarization projector. This experiment has been realized in the laboratory of Dr. Jeff Lundeen at the University of Ottawa. The question that we would like to address during this talk is how one can project onto the state psi2p, which is a general two-photon projection state, and be able to tune the value of all the four coefficients AHH, AHV, AVH, and AVV. But before answering this question, let's try to remind us why we would need to project onto those states. In fact, in many areas of quantum information, it is important to be able to project onto specific two-photon projection state. For example, if you want to perform fundamental tests of quantum mechanics, such as the non-locality of quantum mechanics, you need to be able to project onto the Bell state, which are entangled two-photon projection state, and then test the value of the Bell inequality. In quantum communication, such as in quantum key distribution or quantum teleportation, you also need to be able to project onto those Bell states. Finally, in quantum state estimation or quantum state tomography, in order to reconstruct the state of your system, you need to be able to project onto specific two-photon projection state. Until now, the protocol which have been proposed in order to realize this projection onto two-photon projection state require additional resources such as control NOT gate or ancilla photon. But as you know, as the number of photons in an experiment increases, the difficulty of this experiment increases. That's why what we want to propose is an easy solution which relies only on linear optical elements and which will allow us to project onto both maximally and partially entangled states with an efficiency up to 100%. But before explaining how you can project onto a general two-photon polarization state, let's take a step back and check how you can project onto a one-photon polarization state. The question that we'd like to address in this slide is how you can project onto the state psi-p, which is a general one-photon projection state. To do so, the first ingredient that you will need is a polarizing beam splitter that will implement a projection on the horizontal projection state H. The polarizing beam splitter will leave the state of the system C out in the state H. The probability of successful projection onto H is given by the probability written on the right. If the input state psi in is H, then the probability of successful projection onto H is 1, but if the input state psi in is V, the vertically polarized state, then the probability of projection onto H is 0. Which means that the polarizing beam splitter implements a projection onto the state H. Now the question is, how do you go from a projection onto the state H to a projection onto the state psi-p? To do so, you will need to add half wave plate and quarter wave plate that will be placed before and after the polarizing beam splitter, and that will implement a unitary transformation U. Indeed, a half wave plate and quarter wave plate implement a unitary transformation that can transform any known polarization state into any polarization state, which means that you are able to transform H into psi-p. In the same way as the polarizing beam splitter leaves the system in the state H, the projection onto psi-p will leave the system into psi-p. And the probability of successful projection on psi-p is given by the formula in the middle of the screen. However, if you only care about the measurement of the probability, but you do not care about the output state of the system, then you can remove the second set of half wave plate and quarter wave plate that implement the transformation U dagger. In this case, you implement a measurement that will measure the same probability as a projection onto psi-p, but that will leave the system into the state H. Now that we know how you can project onto any one-photon projection state, let's go back to the main point of this talk and explain how you can project onto a general two-photon projection state. So the first question that we will have to solve is, what is the equivalent of the polarizing beam splitter in the case of the two-photon projector? And the answer to this question is a non-polarizing beam splitter and the use of Angud-Mendel interference. As you know, if you send two perfectly indistinguishable photons, which means that they have the same color, the same polarization, the same spatial mode, and the same arrival time, on two different inputs of a 50-50 beam splitter, they will always bunch, which means that they always leave the beam splitter by the same port. This is the Angst-Mandel effect. The question now is what happens if the photons at the input of the beam splitter have a different polarization, which means that they are distinguishable. In this case, they will have a totally independent behavior, and we have four different possibilities. They can leave the beam splitter by the same port, whether the top or the bottom one, or they can leave the beam splitter by opposite ports. If we post-select on the cases where the photons have anti-bunch, which means that they have left the system from different ports, then we are implementing a projection onto the anti-symmetric singlet state S that has the following expression, 1/2 HV minus VH. We can note that the singlet state S is also the state psi minus one of the four Bell states. Now that we know how to project onto a very specific two-photon projection state, the singlet state S, the question is how do you go from a projection onto S to the projection onto any two-photon projection state? Do you just add local unitaries before the beam splitter in the same way we do for a one-photon projector? The answer to this question is no. By adding local unitaries, you cannot change the degree of entanglement of your two-photon state. The only thing you can do is you can go from your singlet state S or psi minus to any of the three other Bell states. Instead, what you need to do is to introduce polarization-dependent losses to one of the input modes of your beam splitter, and this is done using a variable partially polarizing beam splitter. A variable partially polarizing beam splitter, or VPPBS, allows one to independently control the value of the transmission and reflection coefficient for the H and V polarization. For example, case A, if the transmission of H and V are set to 1, then if the input light is diagonally polarized, it will be totally transmitted by the VPPBS. Case B, if the transmission of H is set to 1/3 and the transmission of V is set to 1, then if the input light is diagonally polarized, 1/3 of the H polarized component will be transmitted and 2/3 will be reflected, but all the V polarized component of the light will be transmitted. And case C, if the transmission of H is 1/3 and the transmission of V is 2/3, then if the input light is diagonally polarized, then 1/3 of the H polarized component will be transmitted and 2/3 of the V polarized component will be transmitted. The VPPBS is realized using a display Sagnac and some liquid crystal to tune the polarization, and if you need more detail about the VPPBS, you can see our paper which has been published in Review of Scientific Instruments. So the transformations that the VPPBS perform, it transforms a state psi into a state TH, H and TV, V, where you can tune TH and TV at will. Now that we know how the VPPBS work, we can go back to our main question, which is how do you go from the projection onto the singlet state to the projection onto any two-photon polarization state? We do so by adding a VPPBS before and after the 50-50 beam splitter in the same mode. Those two VPPBS have the same transmission coefficient for H and for V, and they allow us to project onto the partially integral state psi tilde. Psi tilde is equal to √2 of 1 plus gamma HV minus √2 of 1 minus gamma VH. In short, we have implemented the two-photon projector P2P, which is equal to eta psi tilde, where eta is the efficiency of the scheme and is a function of TH and TV, and gamma is the degree of entanglement of the system and is linked to the concurrence, which is a measurement of entanglement. If gamma is equal to 0, then the state is maximally entangled, and in this case the efficiency of the system is 100%. If gamma is equal to 1, then we have a separable state, and if gamma is between -1 and 1, then it will be a partially entangled state. So given an initial state psi in, then the probability of successful projection is given by the formula written at the bottom of this page. Now, in order to transform the projection onto psi tilde into a projection onto psi2p, what we do is that we add local unitaries u1 and u2 before and after the 50-50 beam splitter that allow us to project onto the state psi2p and that allow us to control any of the value of the four coefficients AHH, AHV, AVH, AVV. Also, in the same way as for the case of the one-photon polarization projector, if you don't need to leave your system into the state psi2p, then you can remove the VPPBS and the local unitaries placed after the 50-50 beam splitter. In this case, the output state of your system will be the singlet state, but the probability of successful projection will remain the same, but your experimental setup will be far easier. It is this configuration that we have implemented in the lab. Now that we know how to realize a general two-photon polarization projector, let's see how we can implement it in the lab. So what we have is photon pair at 18 nanometer, which are produced by parametric Down conversion from a laser at 4 or 5 nanometer. The two-photon polarization projector is at the right. And what we have is a VPPBS with a transmission coefficients TH and TV placed in the top mode, and the 50-50 beam splitter is realized thanks to a fiber beam splitter. We needed to add some polarization compensation to compensate for the unwanted polarization transformation realized by the fiber beam splitter. The photon and the coincidence between the photon are detected using avalanche photodiode APDs. In order to test if the two-photon projector works, the measurement operator pi experimental is reconstructed using detector tomography. Detector tomography will reconstruct the experimental measurement operator by analyzing the statistic of all the input polarization state, HVDA, right-hand circular and left-hand circular, that are sent to the system. Those input polarization states are realized using the half-wave plate and quarter-wave plate in the box detector tomography. Using detector tomography, we have been able to do the reconstruction of the measurement operator pi experimental. On the graph at the right, we plot some of the elements of the matrix of the measurement operator as a function of the transmission control voltage, which controls the transmission coefficients of the VPPBS. As we can see, for all of the elements of the measurement operator, the experimental points are really close to the solid line, which represents the theory. On average, the fidelity of all the measurement operator is 0.95, which means that the two-photon projector worked as expected and is able to perform projection onto two-photon polarization states. Now we know that our two-photon polarization projector works as expected, so let's try to project onto a specific two-photon polarization state. Various experiments test the non-locality of quantum mechanics, such as the violation of a Bell inequality using maximally entangled Bell state, or the RD test using partially entangled state. The way the RD test works is the following. Some parametric Down conversion process will produce a two-photon state, which will be in the partially entangled state psi RD, which is equal to HH plus epsilon VV divided by square root 2 of 1 plus epsilon square. Then you will do measurement of coincidences for specific polarizer angle, for polarizer P1 and polarizer Pi2. And then you will test RD's inequality by computing the sum of the probability for 4 different sets of angle for the polarizer P1 and P2. And if the sum of those probability is lower than 0, then you can claim that the quantum mechanics is non-local. However, what we have implemented in the lab is a reverse RD's test, where all the world of state and measurement are reversed. This means that instead of producing photon pair in the RD state and then measuring coincidences for specific polarization, what we did is that we sent those polarization used to test the coincidences into the two-photon projector. We use the two-photon projector to implement an entangling operation by projecting those two photons onto the RDS test. Then we send all the polarization needed for the RDS test to our system, and we compute the RDS inequality. By plotting the value of the RDS inequality as a function of the delay of the two photons, we see that the inequality reaches -420 when the two photons arrive at the same time at the beam splitter, which means that we get a violation of the RDS inequality by 7 standard deviation, which means that our entangling operation worked and that we have projected on the RDS state, because this state is the one that will be able to violate the RDS inequality. In conclusion, we have presented a new scheme to implement a universal two-photon projector using only linear optic, which allows to project onto maximally or partially entangled state with an efficiency up to 100%. We have then experimentally implemented this two-photon projector and proved that the fidelity of the process is 95%. Finally, we have violated the flipped roll RDS inequality by 7 standard deviation, proving that our system can project onto a specific two-photon state, specifically the RDS state. If you want to know more about this experiment, you can read our preprint on the arXiv, and the manuscript is currently under review. I would like to thank you for your attention. If you want more information about the Lundeen lab, the other experiments we perform, or if you want to join us, please check our website, photonicsquantum.info.